Hello, everyone. Welcome to the Math Magician's Den. This is the Herm Dog, and today we are talking about derivatives again. And what is the derivative of a function? The derivative of a function essentially represents the slope of the tangent line. How do you find slope? You take the change in y over the change in x. And if you watch my previous videos, we went over how to find the change in y was f of x plus delta x minus f of x all over delta x. And here's the thing, if you let that delta x approach 0, it gives you the slope of a tangent line. Now, this process of finding the derivative is called differentiation. So if you ever hear the word differentiation or differentiate, we're asking about finding a derivative. If a function is differentiable at a value x, the derivative exists. If it's differentiable on an open interval from a to b, then the derivative exists at every point on that interval. Now, what we're looking at here, we are looking at different notations. This is f prime of x. That represents the first derivative of f of x. So if you had y equals, y prime would represent the derivative of y. Now this notation, when you put d over dx, that means take the derivative with respect to x of something. If we want to take the derivative of y with respect to x, we use dy dx to represent that. If I want to take the derivative with respect to x of a function, let's say f of x, then I take this notation, the derivative with respect to x of f of x. I rarely use this notation, but this is another notation for derivatives. This is the derivative of y with respect to x. So we could even put the derivative with respect to x of f of x. You might see that notation as well. Now, there is a possibility, and we know this with limits. Limits could actually approach infinity or negative infinity. If that happens, what happens at that value of c, you have a vertical tangent line. Okay, so if you have a limit of this different quotient that approaches infinity or negative infinity, what's happening is that graph is going vertical. You're going to have a vertical tangent line. Okay, now there is an alternative form for the derivative we can use as well. Now remember, I told you to find derivatives, what we're going to do is we're going to take the change in y over the change in x. Now, on a graph, if you have a value c here and another value x, this would be f of c. We could call this point up here f of x and define the slope in between those 2 points. Okay, what we can do is we can draw this secant line, and it would be f of c f of x minus f of c over x minus c. Now, if I let c approach x, or x approach c, I should say, if I let x approach c, what you're going to see is, again, this is going to approach the slope of a tangent line. Now, in order for this limit to exist, we know that the left-hand limit has to be the same as the right-hand limit. And if you've watched my previous videos, you know this. The left-hand limit has to equal the right-hand limit for a limit to exist. And so what we're going to do here is we're going to look at some different functions, and we're going to talk about what the derivative would be at a certain point. Now, the first thing I'm going to do is we're going to look at f of x equals the absolute value of x minus 2, and we're going to discuss its differentiability at 2. So let's take a look at this graph. You'll notice the graph of absolute value of x minus 2 at x equals 2, there's a corner. Okay? So this graph, if I draw it really quickly on here, at x equals 2, it has a corner. So we're going to discuss what the derivative is at a corner. Now, how do I do that? We're going to take the limit as x approaches 2 of f of x, which is the absolute value of x minus 2, minus f of 2. Well, f of 2, if I plug 2 into this, I'm going to get 0, all over x minus the c value, which is 2. Now this reduces, obviously, that 0 is going to just drop out of there. And we're going to have the absolute value of x minus 2 over x minus 2. And what we're going to do is we're going to take a look at two limits. We're going to take a look at the limit from the left, first of all. Now, when you're looking at the limit from the left, pick a number that's just to the left of 2. Let's say maybe like 1.9. 1.9 is really close to 2 on the left-hand side. If I put in 1.9, on the top, I'd get the absolute value of negative 0.1 over 0.1. And if you look at this, this is going to equal 1. I could do this with 1.99. It would still come out to be 1. And I apologize, if I'm coming from the left, this would be negative, this would be negative 1. The slope on the left-hand side is negative 1. Take a look at the graph. On the left-hand side of 2, the slope is negative 1. Now, if I take a look at the right-hand side, the limit as x approaches 2 from the right-hand side of the same function, x minus 2 over the absolute value of x minus 2 over x minus 2. Pick a number just to the right. Let's say maybe 2.1. I'd end up with the absolute value of 0.1 over 0.1. This comes out to be 1. Look at the slope on the right-hand side. It is 1. But we've already said, if the limit from the left-hand side does not equal the limit from the right-hand side, then this limit can't exist. Well, here the limit from the left is negative 1. The limit from the right-hand side is 1. So this limit cannot exist. Okay? So the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2 does not exist. But guys, this is representing the derivative at 2. There is no derivative at a corner. Okay? At a corner, there is no derivative because the derivative did not exist using this limit definition. Okay? Now, I know this next part of this problem here, this got kind of shrunk down. Let's blow it back up. What does the greatest integer function look like? If we go back to Desmos, and I look at the graph of the floor function, what happens with the floor function, we're going to talk about the derivative at one of these integer values. If you look here on this side, all the values are 1 until I get to 2. It jumps up here to 2. Right in between there, if you plug in 2, it's going to jump to 2. Okay? So we're going to do the same thing. We're going to talk about the limit as x approaches 2 on the greatest integer function. This graph goes from a closed to an open circle, closed to an open circle, closed to an open circle. And let's talk about the limit on the left-hand side here. Okay? The limit as x approaches 2 from the left-hand side of the greatest integer function minus the greatest integer function of 2, which is 2, over x minus 2. Now, again, we're going to pick a number that's just to the left of 2. Let's try x equals 1.9 again. The greatest integer function of 1.9 is 1. 1 minus 2 is negative 1. On the bottom, if you plug in 1.9, you get 1.9 minus 2. That's a negative number. Okay? It's a negative number that's approaching 0. The bottom are negative numbers approaching 0. A negative divided by negative is positive. 1 over 0 with respect to limits. This goes to infinity. Now, we already know this limit is not going to exist because on this side, the limit is unbounded. Now, let's just for argument's sake, let's take a look at the right-hand side. The limit as x approaches 2 from the right-hand side of the greatest integer function of x minus 2 over x minus 2. If I plug in a number just to the right of 2, let's say like x equals 2.1, the greatest integer function of 2.1 is 2. 2 minus 2 is 0. The top, ladies and gentlemen, is not approaching 0. It is 0. The bottom is 2.1 minus 2. Well, that's a number that's really close to 0, but it's positive. The bottom is not 0. The bottom is positive numbers approaching 0. This right-hand side actually approaches 0. Now, this limit, this two-sided limit does not exist, okay? Right here, it does not exist because it's unbounded on one side. Okay, so the limit as x approaches 2 of the greatest integer function of x minus 2 over x minus 2, it does not exist. What's going on at x equals 2? There's a discontinuity. There is no derivative at a discontinuity. Okay? So we have two situations where there's no derivative. If you see a corner, there's no derivative. If you see a discontinuity, there's no derivative. Now let's take a look at two more functions here. We're going to do the cube root of x. Now, the cube root of x, we're going to take a look at the derivative at 0. I think all of you can pretty much tell at the cube root of x at 0 right there, that graph is going vertical. My guess is there's not going to be a derivative there, okay? So if I were to take this function and I were to graph it at 0, it looks something like this. So let's look at the limit as x approaches 0 of the cube root of x minus the cube root of 0 over x minus 0. Now those zeros aren't going to make a difference, and let's just take a look at the derivative from the left. The cube root of x divided by x, this would come out to be 1 over x to the 2/3. If I plug 0 into the bottom, I get 0. It's a positive 0 because of the square. This comes out to be infinity. On the left-hand side, if you look at these slopes coming in this way, you can tell those graphs are going vertical. Those points, those tangent lines be going vertical. The limit goes to infinity. Now, I already know this is not going to exist on the left-hand side because it's unbounded, but let's take a look at the right-hand side too. Again, it would be the cube root of x minus 0 over x minus 0. And this time what I'm going to do is I'm going to take a look at the limit from the right. It would be the same exact function. If you plug in 0, you'd get 1 over a positive 0. This also goes to infinity. Look on this side. As you come in, you can tell if I was drawing a tangent line, it's going vertical. Okay? So the limit as x approaches 0 of the cube root of x minus 0 over x minus 0, this does not exist because it goes to infinity. It's unbounded. Okay? So what we have here, we have a vertical tangent line. And what do we know about the derivative at a vertical tangent line? There's no derivative. Because these limits I keep doing represent the derivative here. This represents the derivative at 0. On the previous page, this represented the derivative at 2. This represented the derivative at 2. We found out that the derivative at the corner was undefined. We found out the derivative at a discontinuity is undefined. We found that the derivative at a vertical tangent line is undefined. Now, on this next one, what I'm going to do is, just to save some time, we're going to look at the graph. Notice at 0, there's that crazy point. That's not what we call a corner. That type of point is called a cusp. Okay? So if I were to draw it here at 0, do you notice on the left-hand side, it has negative slopes? On the right-hand side, it has positive slopes. So here, the slope would be negative. Here, the slope would be positive. Well, if the slope on the left-hand side is negative and the slope on the right-hand side is positive, they can't equal each other. So we have here again, if you took the limit as x approached 0 of x to the 2/3 minus f of 0 over x minus 0, what would happen here is I would get 1 over x to the 1/3. If I were to do the limit from the left as x approached 0 from the negative side, this would be 1 over a negative number, and you're taking the cube root, it would be negative, or it'd be 1 over a negative 0. This would be negative infinity. This side approaches negative infinity. The right-hand side, we're going to do the same thing. It approaches positive infinity. So at a cusp, there is no derivative. Okay. If you like this video, please hit the like button. If you want to subscribe to my channel, please subscribe. I'll be posting more videos later. Thanks for listening.